Assalamualaikum and greetings. My name is Muhammad Hafiy bin Yusoff, and today I'll be discussing and presenting on multiple elimination methods for seismic data processing. And before I begin, allow me to close the video for us to see the presentation. For the content of the presentation, I will start with first the introduction, followed by the objective as well as the concept of multiple elimination and history. The third one is literature review, and the last one is the conclusion. In seismic data, the major quantity of multiple energy is related to the broad surface of reflectivity, and then the removal of surface-related multiples is suggested using a method that removes the effect of surface reflectivity from the result. An important feature of this proposed multiple elimination process is that no understanding of the subsurface is needed. And on the other hand, the source signature and the surface reflectivity do need to be provided. In marine seismic data processing, the existence of the free surface related wave phenomena is a common issue. And to extract the surface related multiple from the marine seismic data, the industry have relied heavily on traditional multiple surface methods such as predictive deconvolution and differential move-out filtering over the years. These methods are based on very specific assumptions about the subsurface and difference between primaries and multiples that are distinctive. The usefulness of this approach can be limited because oftenly the expectations are often not be met in the field. Next, we move on to the objective and concept. For current seismic imaging and evaluation technique, multiple reflection have been provided a great challenge. Internal multiples are more difficult to eliminate than surface multiples due to weaker move-out discrimination with primaries, leaving only wave equation-based prediction and subtraction method. The primary evaluation energy is used in the majority of current imaging algorithm. Therefore, in pre-processing phase, multiples need to be removed from the data. There are three internal multiple elimination IME method based on the feedback model, two which are well established, the prediction and subtraction method using back propagated data and surface data, referred to CFP based and surface method based. CFP based is a common focus point. And the third one is the inversion based method, which is the recently expanded from the estimation of primary by sparse inversion, EPSI. And all these three techniques are based on the separation of event from above and below a certain level, after which convolution and correlation predict internal multiples. This method historically began with NC and Newman, Paul Newman and Nigel NC in 1967, who found that primary events were converted into multiple with the auto-convolution of a trace, and Cannon in 1979 suggests a K-W domain inversion scheme to remove multiple in horizontally layered elastic medium. And Berhout in 1982 used a wave theory-based matrix formulation to redefine multiple problem for laterally varying media. And Vishnell in 1989 and Wapanor et al. 1990 produced an adaptive version was shown with example. And the method described based on Berhout approach can handle both single component and multi-component acoustic. The method described based on Berhout approach can handle both single component and multi-component acoustic and elastic data. SRME technique or surface related multiple elimination technique is proposed by Verschoor 1992, Berhout and Verschoor in 1997, Verschoor and Berhout 1997, and Wiglin et al. In 1997, which has proved to be very efficient over the years and one of the significant methods for surface multiple elimination. Widmer and Verschoor in 2013 made an advancement to the technique, which they redefined internal multiple elimination as a method of complete waveform inversion, following the EPSI principle. The internal multiple can be calculated and extracted from the original data by plain substitution in this generalized SP method, which we will talk more later. We move on to lecture review. The first one we are going to discuss is the common focus point based method, which is the internal multiple trend can be projected by convolving three datasets along a depth profile Zn for a particular survey, and this mechanism involved can be defined by this following formula. It is the representation of internal multiple with respect to depth level Zn requires two convolution along level Zn. And for this equation, there's two kind of dataset are needed. The first one is half redatum data with the source at the surface and the receiver below, and the second one is completely redatum data with all sources and receiver placed along the chosen depth level in the subsurface. And in 2005, Burkhardt and Verstio show the two separate kind of data have been referred to as common focus point data, hence this approach called this CFP-based IME method, or common focus point based internal multiple elimination method. And as we can see, CFP-based prediction where internal multiple related to current depth level Zn are predicted by convolving muted CFP gather, the black and the blue ray path, the black and the blue one, and with the time reverse grid point gather, the red ray path. For the step in CFP-based method, the first one is the practical measure is the first thing that are focus operators, which are selected using chosen time and corresponding NMO velocity. And second one is the CFP gather is generated and muted using this focusing operator. The third one, the grid point gather are built by another focusing step to CFP gather without mutes, when the time reversing the non-casual component without rearrangement. The fourth one is the subsurface grid area have all their sources and receiver positioned at the chosen depth. And the last one is finally the internal multiples are predicted by convolving muted CFP gather and time reverse grid point based on the illustration shows previously. And for CFP method, there are elimination precaution, which is the autocorrelation of the source signature is included in the predicted output, which produce the correlated output that are inaccurate. Thus, we need to have adaptive subtraction because it is a supplementary step to the addition process. And in 2005, Burkhardt and Verstio demonstrated that owing to the error calculation, it is necessary to estimate the use residue model because the grid point gather are used in time reverse fashion, though the use of focal operator enable the separation of occurrence from above and below the chosen depth range. Next, we move on to the second method, which is the SRME method, surface related multiple elimination method. Jakubowicz in 1997 suggested which no extrapolation is needed, meaning that on surface data can be used reliably to predict the internal multiples, and convolution can be done along the surface using following expression. And the structure of convolution is very similar to CFP-based prediction, but all the sources and receiver are situated at the surface. The first PN denoted by the blue ray path, and PN denoted by the red dash ray represent primary reflected from the interface below and above depth level Zn, respectively, that have been explained in the first equation. The second one, Pn-1, denoted by the black ray path, represent data with multiples related to the depth level Z0 to Zn-1, remove and also primaries above Zn being removed, as exposed in second equation. And based on this is where the surface data above and below Zn are separated and convolved along with the surface with the dash part-time reverse. Based on Verstio and Burkhardt in 1997, SRME is utilized in three phases. The first stage involves all the elimination of non-physical noise, regularization of the measured data to produce constant grid of sources and receiver, the interpolation of missing near offset and missing intermediate offset, and the removal of the direct wave and its surface reflection. And the second phase is prediction of multiple. The prediction is based on the observation that surface-related multiple can be predicted with temporal and spatial convolution of measured wave field itself, thus can be expected. Lastly, after the subtraction of the multiple, the energy in the seismogram is minimized by using minimum energy criterion, which state that after the subtraction of the multiple, the total energy should be minimized. And compared to CFE-based method where inverse wave field extraporation is involved, the implementation step for the surface-based method are simpler. The first one is data above and below the chosen time level are separated, then internal multiple prediction is performed via convoluted along the surface. And lastly, because of the source signature autocorrelation, the predicted internal multiples are adaptively subtracted from the input data. Next, we move on to the last method, which is the estimation of primaries by sparse inversion (EPSI). One main drawback of data-driven, which is we discussed two methods earlier, is the method are based on prediction and absorption, is that primaries are often not well preserved when internal multiples overlap with primaries. And in 2010, Yima and Verstio has redefined the surface-based internal multiples elimination as a large-scale inversion process that lead to generalized EPSI method. and this based on the work of Grunestein and Virchow in 2009 for the case of surface-related multiples where the primary impulse response are unknown and that are parameterized by spike in the space-time domain. And in addition, the source wavelet is also parameter. And based on the question, where all quantities are related to the surface level Z naught. S represent the average source wavelet for all shot, and Zn and Xn impulse response related to reflector below and above level Zn. The internal multiple term, negative Xn, and P n minus 1 contain no effect of source signature autocorrelation that are inherent in multiples predicted by the CFP-based and surface-based IME method. And in generalized FC, where the primary impulse respond above and below Zn, denoted by the fine rate path, meaning that no wavelet is included and is estimated in full waveform inversion procedure, and multiples can be constructed along the surface using convolution. From the previous statement, therefore, internal multiples can be constructed by generalized FC and can be subtracted from a general data directly. And impulse response Xn and delta Xn and source signature S are unknown that can be estimated by minimizing objective function from the equation where the summation sign indicate a full summation over all sources, receiver, and frequency. For internal multiple elimination, for example, n greater than 0, the initial value for one parameter set need to be known. For example, the source signature S as output of surface multiple removal. Xn, delta Xn as S are updated alternately in iterative procedure. The step is the update of delta Xn for all frequencies is obtained by taking derivative of J with respect to delta Xn. Next, the update is transformed to the time domain where sparseness is imposed by selecting the largest events from per trace. And furthermore, a suitable time window is applied. The window starting with a small size, then increase as iteration number grows. The next one is the sparse and time window update is scaled and added to the current estimate impulse response. The next one, we have the update of Xn is calculated in the same way as delta Xn. Then S is estimated as a filter obtained by least square matching the impulse response Xn plus delta Xn to the following step in the time domain for all shots simultaneously. And lastly, after several tens of iteration, internal multiples related to current depth level n are constructed and can be subtracted from the input data without adaptation. And last but not least is the conclusion, where from the previous study and also investigation, there are two stages in SRME procedure, which is the multiple prediction and adaptive subtraction, in which the subtraction process is supposed to compensate for the error in prediction. And Jakobowitz in 1998 shows that there is no need for such inverse wave field extrapolation and that all convolution at surface level can be carried out directly. This technique is referred to IME, internal multiple elimination approach, centered on surface. Like SRME, the same technique, prediction as obtained is shared by these two IME methods. The limitation of adaptive substitution can be more severe as a result of small move-out discrimination between internal and multiple primary. And in 2009, when Grunestein and Virchow suggested estimating primaries by sparse emission FC, then improved by Figma and Virchow in 2013 to overcome the limitation of adaptive subtraction, where primaries are calculated as unknown in multi-dimensional large-scale inversion method in such a way that the total measured data is clarified along with their corresponding multiples. The key benefit of IFC over SRM is the avoidance of the adaptive subtraction. And with that, I believe that is all from me, Muhammad Hafiy bin Yusoff. Thank you very much for listening.